Yeah, I'm Tim Panton. I'm the CTO at Pipe, and I'm the closing act, I guess. So this is about, it's actually a lot of the themes that we talked about today crop up in this again. It's like WebRTC, machine learning, edge devices. So it's kind of nice, actually, that it is what everybody else has talked about as well. So a couple of news flashes. I don't think this has been recognized enough. This is amazing. Right? WebRTC works in every smartphone. Every single one of you has a smartphone, assuming it's less than 3 years old, where WebRTC works in the default browser. That is actually, it means you're all available for a service that could be delivered zero install. I guess that's kind of what Stadia does, but it's remarkable, and it's what we wanted, and we've done it, and I think that's amazing. The other news flash, and this is kind of for my thing, and again, Stadia proves it, and LifeSize and other people, WebRTC is not just about video conference calls anymore. There's other stuff that we're doing. And the attributes of end-to-end security with no open ports, NAT traversal, low latency, zero install, as I said, and obviously real-time video and audio data. They're all great properties for IoT devices, right? And so that's something that we're, we could think some more about, particularly because that gives you a bunch of privacy benefits as well. And then the third thing that's new, which we kind of touched on earlier, it was mentioned briefly, but there's this new kind of hardware out there, which is basically cheap hardware that sits at the edge that does AI tasks locally on the edge. So it's typically a kind of Linux on quad-core ARM chips with a camera interface, an edge AI chipset, which will run Tensor Flow locally on the device. And then there's kind of GPIO for control and data and whatever from sensors and things. But the really interesting thing about these is that they're sub $200, even in kind of one-off quantities, which translates to roughly 3 days of CPU time on an EC2 P3DN instance, which is their smallest vision processing engine. So if you're going to do a recognition task that's going to run for more than 3 days, it's cheaper to use one of these. And if you've got a million end users out there, this is an interesting mark. So some example boards for this. The BeagleBone AI, it's like $140. Jetson Nano was $150. And the one I'm going to talk about is which is in this, which is Google Coral AI, the Google Coral Edge TPU board. And it's, you can't really see it, but it's on the bottom layer of this. The thing on the top, by the way, is a battery. The black thing isn't a cell phone, it's a battery. People get confused, but anyway. So I learn by playing with stuff. I'm not a very good book learner. I'm much happier messing with something to see what happens. And so I decided I wanted to find out what these things were like. And so I applied for the Autonomous Driving Challenge in Berlin, which is a kind of lightweight thing where a bunch of people get together and race these little robots round a track, and the fastest one round wins. And in fact, the competition I'm in takes place on the 4th of December, so kind of wish me luck. So I decided that I wanted to do this, and I wanted to go for the kind of minimal possible vehicle strategy of lowest investment in time and money. So I decided to reuse this base, because I'd got a bunch of them anyway from a WebRTC IoT workshop that we'd been doing. So I kind of knew about them and the motors and whatever. And the Coral has the same form factor physically, well, similar anyway, and a similar pin out to the Raspberry Pi, which allowed me to kind of bolt it on there pretty easily. I could use the STS Pi existing kind of it has a little local web service that runs in Python on the device, so I could use that to drive the motors, and I could adapt the examples that the Coral people ship with it for the recognition engine, and I'd gather the data by driving. So I wasn't going to kind of build a complicated model. I was just going to drive the thing and collect that data and then push it through a model, a learning engine that would produce a model out the other end. The big decision I made is that I wanted to do through the lens. So I really wanted it to be what you saw on the thing was what it would be learning from. So rather than kind of looking down on it, I would look through the glass, basically, through the camera lens that it would be using. And then to save kind of investment and hassle, I would use Google's Auto Vision ML in the cloud to do the model preparation. So, things aren't ever as easy as you think. The main problem I hit was that the Coral examples are great, but they use a GStreamer pipeline, which I'm kind of reasonably happy with, which creates an H.264 byte stream, which I am reasonably happy with. But they send them over a WebSocket to a browser, and then they decode them in JavaScript, which means that the latency the quality and the latency in that pipeline is not good enough to drive something, and it certainly wasn't going to be good enough for me to win this thing, because what you're going to do is going to be very difficult to correlate my actions with the frame grab. So basically what we're doing is grabbing a frame, tying it to whether I'm driving left or right or forwards. And when you start having latency in that, it's very hard to correlate. So I decided that what I needed to do, and this kind of riffs off what we were saying earlier, is that I need to eliminate the variable latency in this. So I thought, well, hey, we'll use WebRTC. So I thought, well, this isn't a work project, so I should really use libWebRTC. But really, life is too short. It's 23 gigabytes to build, right? I know, okay, that's with all the options. You don't really have to do all of that, but it is big, right? And it's designed, it thinks it's living in the browser, because it is, that's what it's for, right? And in bits of it, actually think they're living in the kernel, the Linux kernel, but that's a kind of whole other story. And it also assumes that you've got a keyboard and a mouse and other stuff around there. And I don't have any of that on there, and I don't need it either. And it's a monolithic thing to work in. It's a big process that you then have to tie everything else into. It doesn't kind of decouple very well. And the other thing that was mentioned earlier is that it moves pretty fast. So maintaining a private branch is an absolute nightmare. And for good reasons. I mean, you want to contribute this stuff back, but for my little noodling project, it doesn't that overhead is expensive. And it's got a pretty complex, and to be honest, unsatisfactory for this task, API surface. So I decided, and I'm kind of biased in this because I had one, I decided to extend my own WebRTC agent. So we'd already written a WebRTC stack for other things, and I thought, well, hey, I'll just extend it a bit to meet my requirements for this. And what I wanted to do was just to proxy all the things I already have and just push them out through the WebRTC agent out through to my smartphone. So that's kind of what we did. We proxied the video RTP. Actually, I'm not using audio on this, but it's the same problem, basically. And proxy HTTP and WebSocket out over it as well, through the WebRTC gate process and out to a smartphone, so I could drive it from a smartphone. This is actually an iPad, but same logic. And then a little bit of configuration to manage what services and users are allowed. So it looks like this. This is a generic one, like it might have a device with a temperature sensor and whatever else would look like this. But there's a kind of weird thing there. Like, why would you proxy HTTP over the data channel? Well, it turns out it's actually a really nice thing to do because, I don't know if you've seen this, but all of these devices that have little local web interfaces, they now say insecure across the browser tab, or you have to install some kind of complicated workaround of trying to get a certificate in there that's from Dyn DNS, and the whole thing is really pretty messy. What's nice about proxying it over the data channel is you don't need to do any of that because it's a locally self-signed certificate, and so that issue doesn't crop up. And interestingly, you end up with quite reasonable latency because although you're layering a protocol there, you're not doing a round trip to a cloud service, and you're not, maybe in this particular case, we'll probably stay on the Wi-Fi. Right? So you get wins and lose and pluses and minuses there, and it turns out to be a net win. And of course, there's privacy benefits, which generally don't matter in a lot of cases, but for these robot cars don't. But if that was a vacuum cleaner, it might. And we do this by abusing the service worker. which is a whole other question. Happy to talk about it afterwards. So in the case of this thing, it's even simpler because actually the camera is the only active sensor in there. So you end up with video coming from the standard Linux video, going up through a GStreamer pipeline, being sent out to the WebRTC agent with a little config, and then coming back, you have the motor driver instructions from the web interface, which then come back down and drive the motor through the GPIO, having hit the Python web service. So what does that mean? And I've kind of explained this already, but the basic thing is that I'm going to drive it around a track, and it's going to store each frame as a separate JPEG, and tag it, each of them, with what I was doing at that time, left, right, or forward. And then I'm going to upload those tagged images to the Google Cloud Service, and we'll generate a model from it. So the learn mode, which is what we'd be doing there, is basically that, where we grab the JPEGs, we push them down into what's laughingly called a corpus, or in this case, a directory, and send in the actions, which are actually just a log file, push them all together, and then we're going to upload that. So this is the nervous bit. We're going to drive this thing. So let's see whether it works first. Come on, you can do it. Oh, come on. Yeah, there we go. So what's interesting about that is just proxied this web. This is a web browser. This is Safari, mobile Safari with WebRTC in it. Thank you. And it's loaded that interface through that proxy I was talking about. So I'm going to click on Learn, and it's going to go into Learn mode. And now we have what's effectively a handheld camera. So now we put it on the track, and I drive it round. Now, I won't actually do a full thing because it turns out that the training takes about 3 hours to run. So even if I collected this, we'd still be running the training model after you'd finished all the wine. So that's probably not a good idea. So I'm going to bring it back to me. I noticed one thing I found that I made a mistake with the first time round is I drove around a very simple track clockwise, and I had never turned left. So there was actually no left-hand data in it. So I then realized that I had to either make a more complicated track or drive around it both ways. So I did that. So now, that's what you end up with. You end up with a pile of frames, which are all tagged with what direction we're going in. And as you can see, it's quite sensitive to the lighting. I actually retrained this for 2 reasons. One of which was the lighting is completely different here from my sitting room. And the other one is that this carpet looks like a video glitch. It looks like the worst kind of video glitch, right? And it completely threw it. So I retrained it this morning. And it did actually genuinely take 2 to 3 hours to train. So now we have a trained model installed on this thing, and we're going to drive it. Well, so how it works is we have basically the same thing that we had before for collecting the data, except that we replace the corpus with an AI process, which takes the frames and says, that looks like a left, that looks like a right, and pushes it to the Python web service. The Python web service then drives the motors. Now, it turns out that's a nice model, but physics intrudes. Right? You've got about 20 centimeters of view forwards. I did have the camera angle up further initially, but then it starts recognizing the furniture rather than the track. So you need to aim down a bit. And then so you've got a run of about 20 centimeters. And all right, not here. I'm not going to do 2 meters a second in here with all you here. But in Berlin, hopefully, in order to win, I'm going to have to go as fast as I can. So 2 meters a second, that only gives you 100 milliseconds before you run out of track. On one of these corners, you've only got 100 milliseconds between arriving on the corner and going off the track. So that's not very long. It's certainly not long enough for a cloud round trip and a bunch of other stuff going on. So, and the camera does like 20 frames a second. So that's 50 milliseconds gone already. So you kind of got to be reasonably fast. And the nice thing is that this Coral will do a recognition every 5 milliseconds, which is fantastically impressive, I think. So what that meant was that I needed to take out some of the latency, which came in from the AI process talking through the Python web service. So what I did is I took the 5 lines of Python that were in the web service, and I plugged them into the Python AI code so that it talks directly to the motors in this version, which took a chunk of latency out. And what was more interesting, actually, it took a bunch of variable latency out, because what I found was that with rapid changes, it was queuing them up. Just GStreamer, mentioned it several times. I kind of have mixed feelings about GStreamer. This is the GStreamer pipeline that you're going to see work. And I don't want you to kind of fixate on it, but there are 2 bits in it. The top piece here is the the stream that's controlling where it's going, down to about here. And then the bottom bit is just the upload to the video so I can watch it driving. So that generates some RTP, which we then send to the pipe agent, which then sends it out to the screen on the iPad here. And what's nice about that is I can watch it going wrong. I can see maybe why it's gone into a complete panic, because I can see its view. So, right, this is the really unnerving bit. So we'll do a live demo. I don't think I've done anything this stupid for a while, actually. Right. I actually don't know why it takes this long at this point. Just to make me nervous, I guess. So now I'm going to press auto. And what you should see is it driving itself around the track. Now, it's actually more interesting, I think. Nope. It's more interesting, I think, to watch it on the screen, because you can see its mistakes. It's really not going to do it today. Oh, come on. Oh, that's better. Go on, go on. Yes, 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 way! And I don't have my hands on the keyboard. It wasn't me. Oh, now you're cheating.
Going back.
And cutting corners. That was a save, that was. Didn't think that was going to work. So this is data that took me about 20 minutes to generate. If I was serious about this, I would obviously generate more data and better data. But you can see that it's kind of doing something that vaguely relates to the track. Stop. So we can play with that later as well. You can all participate in that. So what did I learn from that? Well, I mean, actually, because the whole thing was supposedly a learning exercise, not just to play with track. I learned that edge processing actually is quite low cost, and it's quite fast, and it gives you a low latency, which is kind of interesting. And like the WebRTC gives you a bring your own device. I can actually lend this thing to people, and they can drive it very easily, actually. And it's also through the lens, which I think is important for a lot of cases. I mean, we heard the Phantom guys talking about this. And I just want to say this again. The Edge AI is fast. I don't know if you noticed on the top of the screen there, but it was doing, I think, a recognition every 3 to 5 milliseconds, which is surprisingly quick. But it makes mistakes for completely impenetrable reasons. Like, I don't know why it sometimes works and sometimes doesn't on that track, right? And what that means is that I've got no way of correcting that bias, knowing where that mistake comes from. Like, so unless my training set is totally representative, there's a risk there. So that's the thing we had to think about when we're doing AI. Yeah, and GStreamer pipeline construction is really a dark art. You know, it honestly, getting that pipeline right took me about as long as the rest of the project. But it works. And the other side thing is like the WebRTC bit didn't get in the way. I've actually not talked much about WebRTC. I've not talked about like ICE or anything like that. I didn't need to. It wasn't the point. The point was that I could wrap up existing services and export them. Kind of just did the job. I'm Tim at Pipe. Email me. I'd be happy to talk to you about kind of any of this. There's a GitHub repo which is fairly dynamic and will continue to be dynamic until the 4th of December when I lose the race, and then I may lose interest as well. And as a bonus for you all, which is nothing to do with this, but is to do with WebRTC, I've just done a podcast interview about WebRTC and telehealth, which is actually really interesting because the benefits are not what I expected, right? You know, in rural Australia, telehealth means something quite different from what it does maybe here. I encourage you to listen to it. I say a little bit, not much. Sylvia, who is talking about it, is actually really interesting about it. And of course, I recorded it using WebRTC because you kind of have to. So that's me.